Well, thank you. I'll be moving back to some more geological and big picture aspects here by giving an overview of the impact processes in the early solar system. We know that the whole solar system formed because of collisional processes and impact processes, and so the whole solar system, in terms of planets, is the result of impact processes. When we look at surfaces in the solar system today, it is fairly clear that impact cratering is the most important surface modifying and surface forming geological process even today. And it is easy to infer that it was more important in the past when there were more bodies in between the planets still, and therefore impact cratering has always been a very important geological process even in the past. Now, the accretion of the Earth, of course, happened by collisional processes and was terminated by large-scale impacts. The Moon, for example, anybody looking at the Moon today will notice that it is covered by impact craters so tightly that they're overlapping, and the same is true for Mercury, for parts of Mars, and so on. On Earth, of course, as we just heard before, the geological record pre about 3.8 billion years is very spotty or non-existent. And so when we look at the very early collisional and impact history at the solar system, we really need to look at the Moon, at our closest neighbor. And so there has been, as we heard also yesterday, some evidence that, first of all, there was an intense post-accretionary bombardment history between about 4.5 billion years ago and 3.9 or 3.8 billion years ago. There is a not universally agreed upon line of evidence that there might have been a short and intense late heavy bombardment period at around 3.8, 3.9 billion years ago in the inner solar system. There's some evidence from lunar rocks. There's evidence also from some meteoritic data. For example, Don Bogart published a paper a while ago on the bombardment history of certain meteorite parent bodies. If there was such a late heavy bombardment, or more broadly speaking, for sure there was a heavy bombardment. The question is, was there a spike? But in any case, there were devastating consequences for the Earth at that time. Now, at this point, and this is kind of the roadmap for this talk, we don't really have unequivocal evidence for late heavy bombardment on the early Earth because mainly lack of the rock record. But if I want to look at other impact evidence on Earth in the early history of the Earth, it is very spotty indeed. We have some spheral layers in South Africa and Australia with ages between about 3.5 and 2.5 billion years, and these might represent a few, less than a dozen, probably large-scale impact events. And then the oldest preserved impact crater on Earth is only 2 billion years old, and this is less than half the age of the Earth. So that is a little bit scary. Of course, we know that the currently accepted model for the formation of the Moon has to do with a large impact. In that hypothesis, a large Mars-sized body hit the Earth about 4.5 billion years ago at a time that has been quoted between about 30 and 60 or 80 million years after the T0 formation of the Earth age. The heat involved in this event led to an almost complete rehomogenization of the Earth and lack of siderophile elements and also volatile elements in the resulting lunar body, which is shown here in a series of paintings by Bill Hartman and a few other well-known images. Now, when there was such a large-scale impact event, then it's clear that there was a complete remelting of the Earth, the loss of any primary atmosphere, and that the material that was the core of the impact emerged with that of the Earth. and there was a little bit of material left in the orbit around the Earth from which the Moon formed. So this is a fairly standard picture. Now, let me move to a brief discussion of this supposedly late heavy bombardment period around 3.8, 3.9 billion years ago. It started with a fairly famous paper by Fuertera and colleagues in 1974, which indicated there was a fairly intense bombardment record peaking around 3.9 billion years ago. The question is, was this the end of an intense heavy bombardment period in general, or was there really a peak? The lunar highland crust, of course, formed relatively shortly after the formation of the Moon, and there has been a large number of geochemical and geochronological studies that indicate the presence of brecciated highland samples with melt rocks that are concentrated around 3.8 to 3.9 billion years ago. Now, of course, the more data one gets, the more complicated the story becomes. And about 10 years ago, when especially Graham Ryder was formulating this late heavy bombardment hypothesis together with Brent Dalrymple based on age data, the number of samples, for example, from lunar meteorites was relatively small. This has increased now, and that also has increased the width of the age bracket. Nevertheless, if some of the large basin-forming projectiles accreted onto the Moon at around that time, 3.84 billion years ago, then keeping that part of a steady-state flux would actually make the Moon already not at 4.45, but at 4.1 to 4.2 billion years ago, and that is clearly not the case. So you can argue about a variety of possible flux curves. Yesterday we saw one that seemed to indicate that there was less impact events happening before this heavy bombardment period. That can be argued about, but in general, what we would see is either an increase of the impact activity, or at least a decrease after the late heavy bombardment period, or simply the heavy bombardment period. So until we go back to the Moon and collect a lot more samples with a lot more age data, we're left with looking around on Earth. And here we have the problem that there are very, very few rock sections left that are of that appropriate age. And in fact, it seems that the age that is prominent on the Moon, the 3.8 to 4 billion years, is almost totally lacking on Earth. There's 2 zones that might contain a little bit of record, and none of them has shown to have any evidence of any impact event. Now, there is evidence from neodymium-142 isotopic anomalies that seem to indicate that the Earth mantle had already undergone differentiation at the time of formation of the oldest rock on Earth's surface. That means that the Hadean Earth must have had a fairly thick crust, mostly basaltic, covered by an ocean with minor amounts of felsic rocks. And something like this might be the picture of the Earth about 4.1 billion years ago or so, with impacts, the Moon not yet having its large impact basins and being much closer. So the only rock, quote mark, record left on Earth from the Hadean period is in the form of detrital zircons. There have been a few attempts already to look for shock effects in these Hadean zircons. Maybe that's the place to make clear that those of us studying impact craters rely on 2 main criteria to identify any impact record. The first one is the presence of shock metamorphic effects in minerals that make up the rock record. And zircon, of course, is an accessory mineral that may contain shock effects and has been shown to contain shock effects elsewhere. Quartz probably wouldn't last that long without resetting. And the second major line of evidence is the presence of a meteoritic component. And unfortunately, both of those searches have come up empty so far for rocks from Isua, for example, and also from Hadean zircons, although the search is still ongoing. It is searching for the needle in the haystack. The lower right, there is an image of a chondrite normalized pattern of mostly platinum group and other siderophile elements. If there were a meteoritic component, it should be about a flat line and not one of these big zigzag things. I know some people like to measure just iridium. Measuring iridium out of context without looking at the rest of the geochemistry really is not making any sense at all. So then there was a paper published about 10 years ago by Schoenberg and colleagues who indicated tungsten isotopic anomaly in Isua rocks that they claim showed meteoritic component. This is a little bit surprising because why wouldn't such a major meteorite anomaly show up in platinum group element abundances, which it doesn't, and also tungsten is not a particularly common element in meteorites. So later, a group of us remeasured some of these samples, actually measured some known impact deposits and came up empty-handed, which is what we expected. There was no anomaly at all. And so that casts doubt on the validity of the earlier interpretation. Early life, Minik mentioned that just a moment ago, could have been present even at that time, 4.1, 4.2 billion years ago, because there was sea surface water, and even very large impactors of the size to make a lunar basin would have only evaporated the top 40 meters or so of the Earth's ocean. The ejecta layer in Barberton, for example, or in Australia, 400 or 500 million years after the end of the late heavy bombardment. Here's Barberton. Here are some of these spherules on the right side. On the left side, some of the locations in Australia and in South Africa. Continue over this here. This was shown to be of impact origin by chromium isotopic data, shown on the right side. There's a little bit of a puzzle still left because the iridium contents in some of these impact layers are 5 times those of meteorites, and that is still difficult to explain. No source crater has been found for these impact deposits yet, and it's unclear why these produced a lot of large volumes of spherules, which seem to be almost totally absent of any post-Archean or more recent impact deposits. Let me go back to that here. Oops. So the earliest craters we actually have on Earth are the Vredefort impact structure, which is about 2 billion years ago. South Africa used to be about 300 kilometers in diameter before it was eroded and deformed. And the Sudbury structure, about 1.8 billion years old, which was also eroded and deformed. And recently some ejecta layers have been found with spherules up to almost 1,000 kilometers distance from Sudbury. No ejecta layer has yet been positively identified for Vredefort, although there's a possible candidate in Greenland, and I have a PhD student working on that, and there was a similar layer found in Russia, actually, which we're working on as well, so we'll see how that pans out. So, oops, that was the images of these 2 craters. The lower one is a radar image. Now, this is kind of the summary where I would like to leave you, which is telling us what do we know really about the impact record on Earth for the last, well, for the first half of the Earth history. The oldest crater is younger than half the Earth age, and for the beginning of the whole story, we have almost nothing for the first billion years. Then we have some spheral layers, very few, that indicate impact events between about 3.4 and 2.5 billion years ago, which really leaves us with the kind of unpleasant conclusion that even though impact cratering was a very, very important geological process in the early history of the Earth, we have almost nothing left in terms of a record. So this is still a wide open field of research. Thank you very much.